Okay, let's talk a little bit more about exponential functions. And an exponential function is anything that is a constant to a variable power. The variable power there, it's an exponent, so that means repeated multiplication, right? So like the n is representing how many times we're multiplying the b by itself. As we said earlier, a negative exponent means that it's in the bottom of a fraction, and a rational exponent is a root function. Okay, so this is a decay function. This is a growth function, right? Because it's getting bigger as we read from left to right. It's going down as we read from left to right. This is a horizontal line. So this is why we don't allow the b to be a 1, right? That's just the graph of y equals 1. Domain is all real numbers, range 0 to infinity, not including the 0. It has a horizontal asymptote at y equals 0 because we see we get closer to y equals 0, the x-axis, as we move out on our growth or decay function. So if you're not familiar with some of your rules for dealing with exponents, here they are, right? When we have a like base and two different exponents, we add the exponents. And division, we subtract the exponents. A power to power, we multiply the exponents. And then, of course, the exponents distribute across a multiplication or division. All right, so how are we going to use exponential functions when we're modeling growth or decay? Here is an example. This is a half-life problem. A sample of strontium 90 has a half-life of 25 years. So half of the quantity will disintegrate in 25 years. So we want to develop an expression, m of t, that describes how much remains after t years. Then find the amount remaining after 40 years, and then estimate when it'll reach 5 milligrams. All right, so let's do the first part. So notice that if the half-life is 25 years, half of the quantity will disintegrate in 25 years. So if we start with 24 milligrams, then in 25 years, we'll have half of 24 left. And in 50 years, we'll have half of 24 left. And in 75 years, we'll have half of 24 left. Yeah, and so on, right? So we see the pattern that is emerging here. Every group of 25 years cuts our value in half. So the way that we can summarize that is by saying, if we look at how many groups of 25 we have, that would be t over 25. That's how many times we're cutting the 24 in half. So our function would look like 1 over 2 to the power t divided by 25 times the initial 24 that we started with. Another way to write that, like so. All right, so this is our exponential function. The base is the 1 over 2 to the 1 over 25. So after 40 years, we would plug in t equals 40, and we would come up with about 7.9 milligrams. Graphing on our calculator, we would graph this function in the y equals and the horizontal line, y equals 5, look for the intersection point, and we see that that happens at approximately t equals 57. So our natural exponential function is e to the x, where e is the number 2.71828, so on, right? So this should have a dot on there. It's an irrational number, just like pi is 3.14, so on, so on, so on. E is the irrational number 2.71828, and so on. We use the natural exponential function a lot, so we're going to be writing e to the x for a lot of our items.